Hi, this video discusses the Reset.c application of Chapter 8. This application explores the reset behavior, watchdog timer operation, and some power-saving modes of the PIC24 processor. Once the application begins, several messages are printed before the main menu appears. The first line is our standard welcome message, which is a string produced by the compiler and assigned to the hello_message macro. This string is printed to the PIC24 default serial port by the outString function. The next three lines identify the reset cause, in this case power on, the CPU identifier and silicon revision number, and the active clocking option. All of this information is output by the print reset cause library function. The next line prints the value of the reset count variable, which tracks the number of times that the application has been reset. The reset count variable is declared as persistent, which means that it is not initialized by the C runtime code. If the persistent declaration is not included, then the default behavior by the C runtime code is to initialize the variable to 0. Typically, persistent variables are used to track actions across non-power-on resets. In main, reset count is initialized to 0 if the power-on reset bit is set, indicating that a power-on reset has occurred. If power-on reset has not occurred, then the reset count variable is incremented. The print reset cause function also checks the power-on reset bit to determine what type of reset has occurred and clears the power-on reset bit if it is set. Thus, we need to check the power-on reset bit in main before the print reset cause function is called. A choice menu is printed next, giving different options that are selected by a single input character. This choice menu is printed from within the while1 infinite loop in main by the print menu getChoice function. The first option enables the watchdog timer by setting the software-enabled disable bit of the watchdog timer. Let's exercise this option and see what happens. Note that after the 1 is entered, the menu is reprinted because we went back to the top of the while1 loop. But then, after a short delay, the watchdog timer expires, causing a watchdog timer reset to occur. The reset causes main to be re-entered, printing the welcome message again and incrementing the reset count variable. Observe that our code checks the watchdog timer timeout status bit to determine if a watchdog timer timeout has occurred. If it has, then the watchdog timer is disabled. The timeout interval of the watchdog timer is set by the configuration bits, and our default configuration bits result in a timeout interval of approximately 2 seconds. Option 2 enters sleep mode, which is the most efficient power-saving mode for the PIC24 family. This is entered by executing the power save number 0 assembly language instruction. This mode stops all clocks on the processor except for the independent RC oscillator that drives the watchdog timer. Stopping the CPU clock freezes all registers at their current values and halts execution. This power saving mode reduces current draw from tens of milliamps down to a few microamps. Let's try out this option. When I enter this mode, the program becomes unresponsive since the processor is not executing instructions. There are multiple ways to exit sleep mode. The most common methods are by an interrupt, by a watchdog timer timeout, by a master clear reset, or by a power cycle. Since the watchdog timer is currently disabled, and since our application code has not enabled any interrupts, the only way to exit sleep mode is by a master clear reset or power cycle. I will exercise the master clear reset to wake the processor. Note that this reset causes the main function to be re-entered, printing the welcome message again and incrementing the reset count. Also note that the print reset cause function has correctly identified this reset cause as a master clear reset. Before continuing, note in this screen that I have cycled power on the PIC24 processor, causing reset count to be cleared to 0. Option number 3 enters idle mode, which is another power-saving mode of the PIC24 CPU. This mode differs from sleep mode in that it only stops the clock to the CPU and not to the on-chip peripheral modules. This is useful if you need the peripheral modules to be responsive to external I/O requests, but we'd like to save power by having the CPU stop operation. The idle mode is entered by executing the power save assembly language instruction with an argument of 1. Idle mode is exited in the same manner as sleep mode. I will not demonstrate this menu choice. Option number 4 enables the watchdog timer and then enters sleep mode. As such, it is a combination of choices 1 and 2. Let's execute this menu choice and observe the results. After entering the menu choice, the watchdog timer is enabled and then the CPU enters sleep mode. After a short delay, the watchdog timer expires. Previously, when the watchdog timer expired, a watchdog timer reset occurred. However, when the watchdog timer expires while the CPU is in sleep mode, the CPU wakes up and begins executing instructions at the point where it stopped. So the message, after watchdog timer enable sleep, is printed when the CPU is woken by the watchdog timer expiration. Once this string is printed, the menu is reprinted as the program goes back to the top of the while one loop. However, the watchdog timer is still enabled. When the watchdog timer expires a second time, the CPU is not in sleep mode, so a watchdog timer reset occurs, causing main to be re-entered and the welcome message to be printed again. Recall that in this case, our code disables the watchdog timer so that we do not get continual watchdog timer resets. Choices 5 and 6 exercise a different power saving mode known as Doze Mode. In Doze Mode, the CPU clock frequency is reduced by a divisor value, while the clock to the on-chip peripherals remain unchanged. Choice number 5 divides the CPU clock frequency by 2, while choice number 6 divides it by 128. This mode is useful when using peripherals whose operation depend on maintaining the same clock frequency, such as the serial port module, the UART, whose clock frequency needs to remain unchanged in order to maintain communication. If I select option 5, the CPU clock frequency is reduced by 2, but my serial port program still displays characters correctly, indicating that the baud rate is unchanged. If I were using a multimeter to monitor current draw by the CPU, I would see that the current draw has been reduced. The Doze bits control the Doze Mode divisor value. These bit values are specified in the oscillator section of the PIC24 family reference manual datasheet. Once the divisor bits are set, the Doze mode is enabled by setting the Doze mode enable bit. Option 7 executes a software reset. This is accomplished by executing the assembly language instruction named reset. Observe that executing this option performs a processor reset, causing main to be re-entered and the welcome message to be printed. Observe that the print reset cost function correctly identifies this reset as a software reset. In summary, the reset application is useful for exploring different reset mechanisms and power saving modes on the PIC24 CPU. This concludes this video. Thanks for watching.